Hello. Hi. Good morning, everyone. The ones that are linked to Zoom, can you hear me? Please write something in the chat because I'm not sure I can hear you. So you need, okay. Yes. Okay, perfect. Thank you. Okay. I believe we can start. Okay, so welcome everyone. My name, sorry, if you are connected to Zoom, the person that are connected to Zoom, if you want to ask something, please raise your hand. I'm not sure, can you please do it? Just to see if I get any sign regarding that. Can you please raise your hand to? No, maybe that's not possible. Okay, please then write something in the chat, and please be patient. If I as soon as I notice, I'll ask. Okay, it's strange. Let me check if I can. The speakers connected. Okay, we have speakers over here. Let me check if it's. Oh, it's connected.
I think they are not a link.
Yeah. Okay, so it seems we don't have any. Okay. Okay, so my name is Miguel Nóbrega. I'm a professor at University of Minho in Portugal, and I've been working for a while in this area in the designing polymer processing tools. And the purpose of this session is to show you how we work with on the design of profile extrusion dies, which is mainly the flow work, the tools we use, and the procedures we follow for designing extrusion dies. So please interrupt me whenever you have any question. I hope to have a quite formal session. Okay, so I will start with a brief introduction. I'll start with a brief introduction to the concepts, to the main concepts, for those of you who are not aware of it. Give you a quick example, and then I'll show you all the procedure. We'll do it with basic tools. So mainly, I believe if you are here is because you know what are extrusion lines. Extrusion lines are used to manufacture profiles, and there is an extruder that mainly melts the polymer pellets. Then there is the extrusion die that shapes the material, and after that we need to cool it down to reach again the solid state, and that's done in the calibration cooling system. Afterwards, there is an roll-off that will pull the profile, the already solidified profile, with a predefined velocity. There is a saw that will cut the profiles with the desired length. The main problem, or at least the problem I'll address here in this presentation, is flow balance. What is a flow balance? Usually when we have a profile, the profile comprises different thicknesses, and the material naturally distributes itself in an unbalanced manner. So the thicker sections will have an excess of flow. And that, as is shown in this top movie, doesn't allow to obtain the desired profile. So the flow is known to be unbalanced in that approach. In order to be able to produce the desired profile, we need to design the flow channel in order to obtain an even flow distribution. There are different ways to do it. I'll explain briefly the strategies. But the purpose, or at least what we are doing so far, is instead of doing tests experimentally, what we are doing so far is designing in the computer a trial geometry, test it, assess it, and correct it. Okay, and this is the flow work I will illustrate to you here today to obtain the balanced flow distribution. Strategies to balance flow. There are mainly two strategies. Let's assume we want to obtain this L-shaped profile here with two different thicknesses, and we can design the profile or design the flow channel using two strategies. One is known by the length approach. The length approach is that we have a thicker section upstream in the flow channel, and somehow we are trying to fool the material. So the material will be flowing in that thicker section, and close to the die outlet, the material, the thickness of the channel reduces to the desired thicknesses, and at the end, the purpose is to obtain in both places the same average velocity in both sections. So after that, we have the all off. If you remember, it's right after, is at the end, almost at the end of the extrusion line. It's here. It's the all off that will pull the profile with a constant speed. That means we'll have the same pulling speed in both sections, and we'll obtain the same. Drawdown ratio means the same ratio in both sections. So it means the same kind of orientation in the different sections. There is another strategy. It's called the thickness strategy. On the thickness strategy, what we'll do is that the problem when you have less flow than required, is that after pulling, the section will become thinner, much thinner than we want. So there is a way to do it, is that we increase the thickness of that section and impose there the flow that will allow us to obtain the desired thickness after pulling. Okay, I will not enter into many details comparing these different strategies, but the publications I have listed here in this slide explain and compare the strategies in terms of optimization. The purpose is, to show you that we'll have a flow channel. The flow channel will be changing along the optimization process, and the purpose is to do this, the computer, in the easiest possible way. Okay, just to let you know that different strategies will promote different tools with different performances, different strategies. I have a question. No, it was just yes. With different strategies, and will induce different morphologies to the material, but that will be not covered in this course. The publications I mentioned, if you want to work in the area, explain in detail what happens. Usually, we're solving a steady state problem, incompressible material. So what we do usually is we grab simple foam, and we add to simple foam the energy equation. You find there are many tutorials in internet where, and in the OpenFOAM wiki also, where that teach you how to add the energy equation to simple foam. Also, that will not be covered here in this presentation. And even the problems I'll illustrate will be with simple foam, but this is to let you know that to proper design extrusion dies, we should do it as well. But in 1 hour, it's not possible to illustrate everything here. In order to obtain the material models, we need to use rheology. In this case, I have an illustration that is also documented in a publication that describes that as the data collected by rheometry, we need to use two different techniques for rheometry, capillary rheometry and parallel plate rheometry. Parallel plate to obtain data at low shear rates, capillary rheometry to obtain data at high shear rates, and then fit a model. We do it at different temperatures to obtain also the influence of temperature in viscosity. And then we fit the model and obtain a model that, in this case, a bird carrow model that we use in the solver. Just to give you an example on how this happens in a realistic profile. So we have here, this is a lead covering profile that it looks simple, but is in fact quite difficult because it comprises thicknesses from 0.6 or 0.75 millimeters to 1.5 millimeter, which difficults the design. And this simple profile, when we start working with the company that want to manufacture this profile, they didn't manage to reach a feasible solution experimentally. So by trial and error. And then we started working together in order to redesign the flow channel in order to obtain the desired profile. And here you have an idea of the actual flow channel geometry, the cross section, and the part here. In order to monitor, how do we monitor flow balance? And this is an important detail. In order to monitor flow balance, we divide the cross section into elemental sections, into different elemental sections, and then we'll monitor the flow in each elemental section. The flow, and divide by the area, we get average velocity in each flow section, and then there is an objective function that is defined in this way in order to allow us graphically to see how unbalanced is the flow. And we have here two illustrations. So the objective function defined in this way should tend to 0 when the velocity is fully balanced. So if it was 0 everywhere, we had a perfectly balanced flow. If it's far from 0, means the flow is unbalanced or is worse distributed. And this is an example of unbalanced flow, a better balanced flow. And in order to have just one number, usually we have the total objective function that, sorry, I didn't mention, but this is the partial objective function in each of the elemental sections. And this is the total objective function that is a sum weighted with the area for the different sections. And these numbers give us an idea of how unbalanced is the flow. So what we did at that time for this profile, we made several trials in the computer, and we reached to an improved or better flow channel. And to do it, we even had to use flow separators. So what happens is on the upstream regions of the channel, we separate the flows that are merged right before reaching the die outlet. And you see these effects on the velocity distribution. And by doing this, we're able to obtain the desired profile. Okay. And in fact, the tool operated at the second trial. At the initial trial, it was necessary to make a few corrections, but at the second trial, the tool operated and is still manufacturing this profile for a few years. So this was the initial overview of the flow work, what I call it by the presentation, the introduction, and these are the different steps I will illustrate in this course. So I will start by the geometry generation with the parameterization, mesh generation, how to compute the objective function, run and test, and then illustrate it, how to make the corrections. As is mentioned in the abstract of this course, we'll use open tools. For the geometry generation, I'll show you how to use FreeCAD, how to generate the geometry and parameterize the geometry. For mesh generation, you use CF mesh, so there are not many details over here. It's just generating a regular mesh in Gmesh, and then there is a function object that we use for the compute the objective function on the fly, and the run and test. Okay, it's the running of the problem. So, okay. Not thanking me yet because it didn't finish. So opening FreeCAD to show you we do in FreeCAD. No questions yet? No. So this is the layout of FreeCAD, the interface of FreeCAD, and for that, or to generate part, we need to generate the body. I'll illustrate you. I'll tell you right after how to do it, and then we use the part design is this model of FreeCAD that allow us to generate 3D geometries and put some restrictions in order to obtain the desired system. So I'll create a body here, and then I'll start a sketch to generate the cross section of the system. So I'll ask to generate the geometry on the XY plane. This will be our first geometry, and currently you see the colors. Usually, on the first time you use it, they are not like that. They are white like this. This is the tools you can use to make the drawing. But you can have in a sketch as this one that will be used to generate a 3D geometry. You can have lines that are in construction mode and lines that are in building mode. The building mode is this one where the lines are white, and they will allow you to generate the tools that will be used in future operations to generate the 3D geometry. For the construction mode, they are just helping lines that are supporting the drawing. But okay, I'll use, at least for now, the building mode, and then there are some restrictions when we are designing. You see here, okay, I can draw a line, simple as this one, 2 points, and I was generating. Sorry, selecting and deleting. But I will draw a line that will have as restriction, see the points, will have as restriction this plane or the x-axis, another one in the plane. You will by default create a restriction, a horizontal restriction, and then is over-defined. That's why it changed to orange, because I'm forcing the 2 points to be in this line and also this additional restriction. So I remove that restriction, and now it's okay. So going on with drawing. So it's just a trial, and then I can make the drawing as this one. Okay, another restriction that was not properly done. Okay, I believe that one was not correct, but I'll remove that one. No, maybe this one. Yeah, right now it's okay. And let me check. It's a bit lagging the computer. Yeah, they are not connected, but I'll select both and I'll force coincidence. I will add a coincidence constraint. Sorry. The main purpose here. Okay. If I press too much, let me delete the last. What happened? Is complaining, and right now, okay, I have constraints over here, and I'll delete. Maybe it's the last one, yeah, because I want this and this to be coincident. Or maybe I have another limitation. Let me check. Okay. Okay. I'll remove then the that's that. Don't have any. I might have extra. Large this one. Check. Okay. It was some coincidence there. Okay, but now I can force it to be vertical. This one is already vertical. This one must be vertical. So I'll put the restrictions afterwards. And now I will add a length restriction. This one is 15. Okay. This one is 2 millimeters. Okay. And this one must be horizontal. Also this one. Okay. Put it close to this line. I want to have a length restriction of 10. Now I can zoom it and okay, I'll make it, because this one I will not parameterize. This one, just to give an idea of how to parameterize. This one, okay, this one I put 2, it should be 1.5 to make it thinner than required. And for this one, I'll make 2 millimeters. Let me check how I'm going with time. Okay, running out of time for this. So to be sure, this one is in the middle, and that's what I want. I will draw a construction line, and now I can use a construction line that will join this point and this point, and then another one that joins this point and this one. Okay, it complained again because it has extra horizontal restrictions, more than the ones I'm supposed to have. But now I choose this, and I'll use the equality. Sorry. No, so I didn't use. When I press too much escape, it leaves the sketch. So I need to choose this one, and then it's equal. Yeah, right now, see, it's green, so it means it's fully defined. Now I have just this restriction is the distance. So, and I'll do the distance between this point, the horizontal, and this point, and I'll put 7.5 to make it easier. So we have a fully defined sketch. To create parameters, and I'll show just with one parameter. If you open this line, we have here a name. So let's call it T4. This way, the geometry will be parameterized. So I'll close, and I can create an extruded object for this size, okay? And in this case, I'll use 20 millimeters. Okay, this will be the last part of the die. And in here, we have the operations we use to create this sketch. And if you remember, that name I added, it's here. So I give a name to the dimension, and I don't need to edit the cross section to change. If I come here and change it to 4, see, immediately it reached it has the information, and I will not be able to, let me check that. I will not be able to enter in many more details. I will open the geometry and show you how I created the geometry, because then we need to create a new plane, connect both sections with the loft, and then there is an important detail that is the division. We do the division over here, but I'll show you the operations in a geometry I've already created, and then obviously the geometry I'll be able to share with you. So I'll open it. Okay, maybe let me to is anyone? No, no one is asking. So GeoTDI finished. I open this one, and here I have the TDI finished in FreeCAD. It allows it's not a very user-friendly tool, but it's quite powerful in terms of the way you are creating the geometry. Okay. So do I have another FreeCAD open? Yeah. It's taking a while. Okay, we have here the geometry mainly. Okay, you can see that. Okay, let me. You can see that I started the geometry exactly in the same way by creating this pad. Then what I did, I created another plane there. Then I used the additive manufacturing, additive loft, sorry. Let me hide these ones. I created the additive loft So first this one, then the additive loft. Additive loft is the tool. Let me show you the tool. Part design is the tool that allows to join different cross sections. And what I did is it was a circle, this circle with this cross section. And okay, at the end we got this. And then I just added a new extrusion to create the remaining of the channel. The next step that is important is in order to generate the STL, we need to divide the outer surface into the different patches that will be used afterwards in OpenFOAM. And to do it, I use this one, this binder. And to use the binder, I select the section, create the binder. There is one detail I didn't mention yet is how to cut. And what I did is that I created in this face the sketch that will allow me to cut this geometry. And at the end I used the tool slice that is available in the part model. There is a slice tool. Okay. Over here, slice to compound. And if you see, using the body I created and this sketch, we have now the slice, see, with different sections, with different elemental sections. Okay. So at the end, we have this geometry and we start creating, we select one and we save it as an STL. Okay. In FreeCAD, in order to save it as an STL, so save as, sorry, it's not save as. File, export, and we export it as an STL. We have already here the different STLs for the different cross sections, and we need to save it as an ASCII file in order to allow joining it afterwards. And so in order to save it in ASCII file, we need to use the extension AST. So in this case, it would be elemental section 1. Yes.
But you can choose which orientation you want.
Here, I believe you don't have control to it. It might here you don't have.
Might be nonsense orientation.
It will not. It will create for each STL a coherent orientation. I never faced that problems. I faced that problem in different geometries, and in order to correct it, I go to Blender usually. And I add all STLs in Blender, and I ask him compute the normals, recompute the normals, and we'll do it in a coherent manner. With the surface, so
it's a small online.
Yeah, I'm not aware of it, but
you just point
to the STL and we'll
some point outside.
Yeah.
And then you will orient the normals towards that point.
But to be honest, I never, using this flow work, I never faced any problems with orientation. I believe is creating the normals pointing outwards as desired. Yeah. But usually when I have problems with other geometries we are working with more, I would say, more complex geometries, and sometimes they are mixed and it has problems, and we do that, isn't it, Rita, with the Blender? This is the tool we use to correct the geometries. But okay, thank you for the recommendation. I'll check it, because the next step would be join these different STLs.
I think you also have this kind of tool because you have many tools in OpenFOAM which are called surface something, and they manage STL files.
But
at least in the OpenFOAM OpenCV version.
Yeah, but for that one we use one of those tools that joins. We have a whole run script that I don't have here now.
Because I know that the orientation can be an issue. I mean, if you use Snappy, you can detect edges where there are not edges.
Yeah, but this is there are not edges because they are flipped. Yeah,
it's just because the normals are on the wrong way.
Okay, I don't have a lot of, but usually, let me show you. Oh, maybe I can show you even over here. Let me check. No, I don't have here. So we use this script, unique STL, that what it does is it joins different STLs in order to create a new. So it's the surface add. We use this tool, the surface add, this utility that will add different STLs together. Okay, and then we use this one to detect the edges, but this one is for CF mesh that will generate the FMS to detect the edges.
There is one equivalent for that.
Yeah. Okay. Yeah. Okay. Yeah. In this case, we use the but okay. Maybe skipping. So the step would be create the different STLs. Okay. And in this case, after generating them with the AST format, just change the name, just rename to STL. And then I use this utility to join them in different STLs. In just one STL, the total STL that contains all the information. We can see. I can open it in ParaView here. I didn't mention as well, but I'm using Windows Subsystem Linux to work, and it works quite okay. Okay, so see, this is the different STL, and in this case, we have the wall. The wall is divided into two walls to assure that if we do that, it's easy for the mesh generation to generate sharp edges. Yeah. Yeah. And so we have the inlet and we have the outlet divided into four, in this case, 4 elemental sections. Okay. This is the STL. Then the total STL, it would generate with that utility I mentioned. So it's the surface feature edges. It grabs the STL and generates the FMS file that is compatible, that is appropriate for CF mesh, and we generate the mesh there, directly the mesh there. So at the end, and I can go. Okay, we have the case here. We generate here the mesh. Since I made the drawing into millimeters, I will delete this file. If we have the drawing in millimeters, we have to convert it with the scale from millimeters to meters, and we have the case ready to be run. Okay. One important detail is how to compute the objective function, and I'll show you what we do. I showed you before the beginning the equation, and mainly we prepare the function object that does it. For that, we need to have the areas and the fluxes at the different elemental sections. So here it's creating a surface scalar field. So it's a reference to the phi that is available in OpenFOAM. It's the flux, okay? Then we have a dynamic list to store the different flows, areas, and the different objective functions of the different elemental sections. It's computing, going through all the patches and storing the patch ID. So it's trying to find the patch ID. There is one detail I missed. Let me show you. It's here in control dict. So we have the function. In the function, we add in the function object parameters, we add the number of elemental sections. So you will look for elemental section 0, in this case 0 to 4. And if it doesn't exist, you will throw an error. If not, it starts computing the flow, the area. Will be appending the data to the vector, to the array, to the indexed variable. Then at the end, with the sum, it computes the average velocity, and then it starts computing the objective function as I showed you in the beginning of the applications. Okay, average area for local average area for a specific elemental section. Then okay, this one is part of the expression, and then this is the maximum between the two. So it computes and stores the objective function of a specific elemental section, computes the contribution of the total objective function weighted with the area, as I showed you, and then divides the value of the total objective function by the area, and then it writes to a file. Okay. So at the end, we have something like that. I can provide that. So I'm writing because to show it in a reasonable time frame, I'm writing that I'm writing all the time steps, so it will write a lot of data, but then the file that is generated here contains okay, it's already, so she's storing number of elemental sections, objective function values for all elemental sections, the total objective function, and the average velocity. Okay, let me reduce this one. It doesn't update, just updates when I change file. Let me check.
I also had a question regarding the energy equation that you have in the system. Did you have it in your function object, or is it?
No, here it's not implemented, but usually you create a solver. We add a solver. Yeah, yeah, so, yeah. Usually this is the approach we use. And then, okay, we can monitor convergence by checking how the objective function evolves a long time. And when it stabilizes, we can stop the calculation and check. So which are the, in this case, what we are seeing is that elemental section 1, 2, and 3 has an slightly excess of flow, especially the second one, and the third, that is the thinner one, has the smaller flow. So we can go to the geometry, change that one, and change the thickness and repeat the process. Okay. So it's advancing. We can wait for some time until it converges to stabilized values. Okay. And mainly, these allow us to check how. Okay. We might need to wait we'll have to wait a bit more time to reach convergence. But okay, I'll stop. Here the calculation, and let me not this one. Here is the geometry. Run. OpenFOAM course. Case. And we can check the results. We'll see that, okay, there is a small flow on the thinner section, but that had to be corrected, and then we could adjust it to reach the desired geometry. And sorry, I opened the wrong file. Yeah. I should open this one. Okay, if I put it on the last time step, you can see the pressure evolution, the velocity evolution, and we can see clearly that there is an excess of flow in the thicker section, less flow in the thinner section, as expected, because okay, this one was forced to be thinner than the others. And then, okay, we go to the geometry, correct. It's already, when I created the geometry, I created already the parameter that will allow to change it, and it changes. So if I go to the sketch, okay, this is not the one. So everything is parameterized. So first, yeah. Let me do is this one. Everything is parameterized, so we change that parameter and the geometry adapts accordingly. So creating the first one requires some effort, but then everything is quite easy to correct. And even the division and the identification of the sections were, okay, so if I go to this patch, there was a constraint. This one that was 1.5. If I change it to 2, yeah. Yeah, right now it changed everything. Yeah. And everything is parameterized, so it's easy to, much easier to generate a new geometry and correct, and then run again and do the test. Okay. And mainly this is it. So this is the procedure we follow to do this. So if the geometry is more complex, it requires different parameters. I didn't show the length, the length approximation, and we do it as well. It becomes FreeCAD is okay. It allows us to do it. Is not the most easier tool to use, but as long as you understand the way it operates, it's quite powerful. So it allows to generate a lot of information, and then the geometry will be parameterized. There are many features in FreeCAD we are not using yet, but okay, I believe it's worth the exploration to understand it, how it works. I don't know if there are questions.
What's the optimization approach? Does it mean how do you run this model when you see it's not how do you decide what to change? Is it just based on
the objective functions, that graph I showed you, Philip?
So you have an objective function.
Yeah.
So you can quantify the objective function.
Yeah.
Now what do you change? How much do you change? What is there an algorithm? As in, like, are you using like generic algorithms?
Philip, in the past, I used the approaches like simplex method to do it. Currently, we are not doing in automatic manner so far.
So you just do it based on experience.
Yeah.
It's more efficient. Just
Yeah.
run the model.
So far, in these examples, we are doing it. We have currently a project with Joel Guerrero from Wolf Dynamics that aims to put here some optimization, closed loop optimization in this approach. But okay, the main problem is that it's not easy to parameterize the generalized geometry, and but we are trying to figure out ways how to do it. In this approach, we have been able. We're porting the experience that we have experimental experience to the doing it in a computer base. In the past, I've used simplex method to do it in simpler geometries. That the movies I showed you here, these tools were optimized, or these tools were optimized with two different approaches. Genetic algorithm is not acceptable. It's too much. It requires too many calculations to have a result. We even
whatever the MATLAB one is in my case, something that's like a local based approach, just samples.
Yeah. Yeah. I'm not aware of that one, but we tried a few approaches. We managed to, even with the simplex method, we managed to obtain results in a reasonable calculation time by starting with very coarse meshes, and then as we're approaching the solution, we're refining the mesh, and we did it. And for that one, it worked okay. In these more complex problems we have been working with, we do it mainly based on the experience.
For your objective function, the definition of it will be discontinuous gradient of it as you approach zero.
This one.
If you change something too much, then it's like you plot the objective function, so it's discontinuous. If you just square that, you get a smooth definition.
Yeah.
This doesn't make any difference for doing it manually, but I know for some of these, anything that estimates the gradient, it will struggle to convert.
Okay.
Struggle sometimes to optimization.
Yeah, but this one is when you mention discontinuous, it means because this one it's always positive and it tends to zero.
It's positive, but as you approach zero,
yeah,
it will hit zero.
Yeah.
And then it will change direction. It will just degrade. The slope will go back. So you square that.
Okay. Okay. You get a smooth change. Okay. That makes it easier for the. Thank you. Thank you for the. Yeah. You're right.
Absolute error. They won't merge.
Mm-hmm. Okay. Yeah. Anyway, okay, this is the approach we are, as I mentioned, there is currently a project with Joel, and we are trying to, for realistic tools, we are trying to have come up with a more automatic approach. but it's due to the complexity of the problems we have in hands is not quite straightforward, and we might be able to reach the something that is feasible based on assuming that the parameters of the tool are identified by someone with experience. Usually that one works well. Persons that have experience on designing the tools, they know at least what they would change if they do it experimentally. So we're trying to port that knowledge to this optimization. Hopefully we'll come up. We need to come up with something that at least will improve the level of automation in these studies.
Are there any problems where elastic deformation is you can't solve at the moment?
There are, especially if you have a complex tool, because I didn't show, no, I don't have here any. When you have inner sections, so all sections, the inner tool might tend to deform in some cases, but we never reached that point. And I understand the purpose of and it would be a good next step, especially when you are manufacturing very small, where you don't have a lot of space to hold that part inside. I remember one of the first tool I designed it many years ago, and at that point we were using our in-house software. Had those problems, and then it was a bit difficult to hold what you call the torpedoes inside the tool. And this might be a feasible and important study to be made. But usually, when we're trying to do this in industry, they take about, if they do it experimentally, they take about 2 to 3 weeks for each trial. So in machining and so on. So they just accept to do this if do it much faster. And you are able, instead of doing just one trial, you are able to do in the computer a few trials before test again experimentally. So we need to find a balance between the calculation time we need to come up with a new solution and what they have. Obviously, if at the end we need just 1-2 trials to do it, or no trials, so just if it's work, that's for them it's important. And this is one of the purposes. The project I just mentioned with Joel Guerreiro from Wolf Dynamics, and it's a Portuguese company, Soprefa, the company I've been working with for many years. It aims to show that, to at least to assess that, if we are how much time and resources we can save by using the computer and the different approaches. So in a manual optimization approach, as I showed you today, or in something more automatic. All the problems we have in hands to solve, they don't face the issue you mentioned, but there are cases in industry where it's required, especially for detailed profiles. And the thickness affects a lot the flow distribution, because the restriction promoted by the thickness depends on, in simple geometry, is on the square of the thickness. So in those cases, changes on that are important. Okay. Don't know if there are any other questions. Yes, please.
What I didn't understand, you have your profile,
yeah,
that you want to generate, that you want to optimize the flows in the end of the production line.
Yeah.
That one is fixed, no? You have your circle.
Yeah.
You have a loft to another cross section, and then your final one, and you optimize the middle one, no?
It depends. In this case, I don't see, you can the outlet cross section doesn't have to be the exact cross section you want to obtain. If the flow emerges from this thickness at a lower velocity, then it will be pulled, so it will be stretched, and it can reach the thickness you want, providing you place in that section the proper flow. Okay, that allows you to do that. It's possible. It doesn't have, and these tools. Okay, here you don't see the details, but they were optimized with the different approaches. And sorry, this tool was optimized with different approaches. Here we are not seeing both. But it's possible to optimize by forcing the cross-section to remain constant, don't change it, and look for the restriction of the flow channel that allows to place in the specific location the flow you need, or the other one. Okay, you're welcome. In this, it was not possible to enter in the details. In these publications, there are all the details, because if you do it with a specific strategy, you get more sensitive tools and so on. Bruno, you want to come to prepare your? Please join and prepare your setup. I believe we'll face a problem. You don't remember the password to connect to the, because you need to share. Okay. So guys, so I'll finish. Thank you very much for attending. The ones that are in the room and the ones that are online. Okay, if you have any other questions, please feel free to reach me. Okay, bye-bye.